My screen is visible.
Yes, sir.
Okay. So in the last class, we have seen the basics and reviews of fluid mechanics. So in order to understand the advances of fluid mechanics, what the complex flows can be written in more complex algebraic ways or equations. Uh, so there is something called tensor notation that would help ease our mathematical uh, cumbersomeness. So we can have large equations and so many components I need to write. So this particular tensor notation, which we are going to talk in this particular chapter, chapter 2, and this would be essential for our future chapters to understand it better. Okay. And this is also essential because we can actually write those larger equations and so many components that I'm going to write, like tau 1 2 tau 2 3, so on, all sorts of components I'm going to write in my equations, and we are going to just use our tensor notations such as ij or k kj or something. We will look into in details in this particular chapter, and this would be the starting step towards the understanding of more complex equations associated with fluid mechanics, so to say. Okay, so we are going to look into the tensor notations and its algebra. So this chapter includes or starts with scalar and vectors, which is this is nothing but this is also called zero order tensor or zero rank tensor. So essentially, scalar is also a tensor, but it's zero order tensor. Vector is a first order tensor. And since from our high school we are well equipped with these vector multiplication, vector, all sorts of vector algebras, and in turn we are comfortable in writing first order tensors from our high schools. But when we go beyond this, second order tensor, and we are going to stuck. Okay, so this is what our more emphasis in this particular chapter. We need to understand this second order tensors, and obviously the physicist, which may they may go till third order tensors and so on, fourth order, but we are not going to look more detail on these third and fourth order tensors, but we will definitely look in second order tensors, since most of our fluid mechanics problems is encountered by these second order tensors such as stress tensors, strain tensors, and all. Okay, next thing we will talk about is the rotation of axis, formal definition of vector. We'll talk about vectors a bit, and then we can move into the real tensors, which we are going to talk about. The second order tensors we will talk. Once we are equipped with first order tensor, we are well in the words to go to understand the second order tensor, and all sorts of rotation of axis we'll see in this particular chapter. Next we will see the multiplication of matrices and how it is written in terms of tensor notation. The notation which we also use here, sometimes also called Einstein notations. Okay, okay, then we will look into the example of second order tensor, more algebra on it. Then contraction and multiplication, there is something called some algebraic application called multiplication. This contraction is also sort of multiplication, but it's not exactly multiplication. We'll see what it is. Then we'll look on to the forces on a surface. Once we understand, so till this far we will be going to understand what my second order tensor is, and then with the help of this we are going to now look the forces on a surface with the help of second order notations or tensor notations. There is an alternate way of looking at these tensors called canonical delta notations, and we will also look into that a bit detail. Next, we will take up a few other uh, vector calculus things such as dot and cross product, gradient, divergence, and curl in the form of tensor notations. Okay, and lastly, we will take up two theorems, Gauss theorem and Stokes theorem, which would be uh, helpful to understand fluid mechanics better in our subsequent chapters. Uh, just in the light of tensors, we'll look these two theorems as well. Okay, and then this will conclude our chapter 2. So let's proceed with the basics of tensor or basic definition. Although it won't, you guys will not be able to understand this particular definition of tensor, but no worries. We will actually look at this thing very carefully one by one. Start with scalar, vector, and then we will move into the tensor. But let me, since this is a formal class, beginning of the class, so I should put a formal definition of tensor so that you should keep this thing in your mind. Okay, but you may not be understanding fully, but I'll have my words that you will understand every bit once I cover this chapter. So the formal definition of tensor is in an m-dimensional space. So m-dimensional. So currently in this particular course, we are going to seek 3-dimensional space, right? 3D space. Okay, so it has x, comma y, comma z. So it has not more than 3 dimensions. So it is a more generalized way or generic definition of a tensor. So in a 3-dimensional space, the tensor of rank n. So let's suppose the tensor is having rank n. It can take value 0, it can take value 1, it can take value 2, and so on. So let's suppose I am talking about rank 2. So in m-dimensional space, the tensor of rank 2 is a mathematical object that has m to the power n components. This is important, and obeys certain transformation rules. And what are those transformation rules? This will be clear in subsequent slides. Otherwise, it is just a matrix. Okay, if it does not obey transformation rule, it is just a matrix. It is just a collection of number. Matrix is just a collection of number. But in order to be it in the form of tensor, it should have n components and it should obey certain transformation rules. It should go under some linear transformation or some sort of transformations. Okay, we'll see in a bit later. So what I told that your scalar is a 0-order tensor. How? Let's validate from here. So the tensor of rank n. So let's suppose my n is equal to 0. I'm talking about scalar. Okay. So how many components a scalar have? Let's suppose you have a temperature field. So you specify a temperature at particular point is T is equal to 27 degrees C. So it is just specified by magnitude. It does not need direction. Okay, so it has only one basis vector. Sorry, it has 0 basis vector. What does I mean by basis vector? When I talk about vector, it will be clear. For vectors, vector is a first order tensor. Okay, so for first order tensor, your n is 1. Okay, so when n is 1 is a mathematical object that has m to the power n components, and I am working in, let's suppose I am working in 3-dimensional space. Okay, we may, though physicists when you talk about relativity in physics, you may go till four dimension. Your space and time x, y, z and time are interwoven, so you have to take four-dimensional spaces that time, and you need to work in fourth-dimensional spaces, and then your things will be more complicated. But we are not going to talk about it in this particular course. We are going to deal with three-dimensional spaces. So my m is equal to 3. Now we also know that for vector, you have, if you are in three dimension, you have three components, right? So let's suppose I am talking about some vector. Let's suppose I have 5i plus 6j plus 7k, and this is my velocity vector in meter per second. Okay, so it has, you can see that it has three components. How does it come here? So it is called rank 1 tensor if it is having m to the power n is equal to 3. You can see here you have m is equal to 3 here, from here m is equal to 3 to the power n is equal to 1. Okay, in similar fashion for scalar, so you have three components, means three components means you have three basis vectors I, comma j, comma k. These are the three basis vector based on which you have decided your velocity in three-dimensional space. But when you talk about temperature or pressure, or not pressure, your density or something, some scalar thing, you don't have to specify any components. So that's why you have zero basis vector. And since this is zero basis vector, so its n will be 0, and now 3 to the power 0 is equal to 1 is the number of components you have. And you can see it has only one component, that is 27 degrees C, or 25 kg per meter cube. Okay, it has only one component to completely specify this particular object. This temperature object can be specified completely by one component. This velocity vector is completely specified by three components, like this. Okay, and this is why m to the power n, when we do that, n comes out to be 1, and hence it is first order tensor, and hence this is zeroth order tensor. Okay, so essentially scalars and vectors are also a type of tensors. So don't confuse it. I mean, you guys might not be aware of this, but yes, scalars and vectors are tensors. Okay, it's a mathematical object. And also, so I have talked about m to the power n components so far, but I didn't talk about obey certain transformation rules. So this will be clear once I reach certain slides. Then you will see that it also, these vectors also obeys some transformation rules, such as whenever, so let me clear that. Let's suppose I have a u velocity. It has some component in your I, j, k coordinate system, and when you rotate this I, j, k to I dash, j dash and k dash, okay, then you see that your u vector is invariant to the coordinate transformation, but its components changes accordingly. Okay, now if you have 5i plus 6j plus 7k here for you, in I dash, j dash, k dash, you may have, this will be the same vector, but in I dash component you may have 2.5 I dash plus minus maybe 5.6 j dash and plus 70 k dash. I don't know, some transformation may happen, but it points to the same u vector. Okay, so this undergoes a transformation, so it obeys certain transformation rules. Okay, so it is evident that vectors have some transformation rules, it obeys some transformation rules. Okay, so these two things are clear, right? So I mean, with these arguments, I can say that these vectors and scalars are actually a tensor, which is zero order and first order respectively. Now let's talk about. So this is what I have written it again. So a scalar is a quantity that is completely specified by magnitude only, and it needs zero basis vector and which has zero rank, which is also called zero rank tensor. Vector is a quantity that has a magnitude and direction and can be completely described by its components along three specified coordinate direction. If you are working in three-dimensional space, if you are working in four-dimensional space, you need to specify four components: I, J, K, and L also. Which in relativity theory, if you would have done any relativity courses in physics, you should have you should be dealing with in four dimensions: x, y, z, and t also. So that time you need to be careful. Okay, but here in this particular course we are not going to deal with this. So this is has only three. It has to specify. We have to specify only three components in order to specify completely, and it needs one basis vector. Okay, which basis vector? It should have one basis vector, that is only one basis vector unit, I, j, k, and it has three components. You can see that in three-dimensional space you have one basis vector, so you should have three components. Okay, now let's talk about in detail of we have seen zeroth order and first order. Now we should talk about second order tensor in detail. So second order tensor in principle with the similar argument, it will have, if we are working in three-dimensional space, then the second order tensor will have 3 to the power 2 components. So this should have 9 components to completely specify that object or that quantity. Right, now you should have three formulas. You see that for scalar you should have only one component. For vector, if you are working in 3D, three components need, and for tensors, for second order tensors. So basically this is a misnomer that we call this tensor. So basically this is second order. You should always write second order tensor, not just tensor, because these also are tensors. Okay, so second order tensors needs 9 components to completely specify. So one such example of 9 component, having associated with 9 component, is a stress tensor, which is widely used in our fluid mechanics. Not only fluid mechanics, in solid mechanics also. Okay, when you try to denote your stresses on a point, then you should have at least 9 components. Then only you will specify that, okay, now I have specified my things. How? Let's see an example. Let's see how. Let's suppose I have a cubical block, and so stress is basically क्या? Stress is force per unit area, but this will give me just one thing, like one unit, one component. Okay, but actually this should have 9 components to completely specify. I'm again and again I'm telling you, in order to completely specify the stress on a point, you should have 9 components. Okay, not just one, just force per unit area. Why? It will be clear in just a minute. Let's suppose I have some inside point, that is here. I have a point O, and I want to, in between somewhere, and I want to specify my stresses on point O. What should you should do? So in order to specify it, what I am going to do, I am going to cut a plane. So I will cut a plane to see the area where it was working and the direction where the force can be working. So you should know the force, where the force is working, and on what area it was working, right? So to completely specify, actually we not only have to cut a plane, but we have to cut 3 planes. Okay, in order to completely specify or see those areas and directions. Okay, so one such plane is this plane. Second plane is this plane, and third plane is this plane. Okay, I messed it up slightly. So this and this. Okay, and then you will be able to completely specify this O point. Okay, so when I cut in this particular way, let's suppose I am taking this particular way, so it will be divided into 2 parts. Let's see. So it will be all these cut sections, I will show it here. So first, when I specify, so let's suppose this is my X, this is my Y, this is my Z. Okay, so now when I am cutting it, okay, so when I'm cutting it, I can see, so this is my leftover cube there, and this, now I can see this O point here. Okay, and now at this point, now I have area, it is the exposed area, and this area is what area? Is the area normal? How the area is being defined? So area is defined as the magnitude of that particular area associated with the direction at which the normal was facing. Okay, so normal was facing in Z direction. Okay, or we can look things into this perspective. So we can think that there will be a force that is, let's suppose P force or F force, or let's suppose tau itself, tau, that is acting in Z direction, and also area was Z direction. Okay, also you can see that this has tau X direction, it is acting, and the area was Z direction. Also you can see that it was acting Y direction, but the area it was acting at Z direction. Okay, so now you got 3 partial components, but you have not completely specified all the planes. In the next plane, let me show the next plane. when we have cut this thing this way, let's suppose this, okay, so you have something, let me draw it this way, this way, okay. Now you have the exposed area, x, y, z. So here things are acting at x direction and area was in x direction. This was acting in y direction and the area was x direction, and this was acting in z direction and the area was x direction. So area, what is the area? Area that is pointing it in the x direction only. This is a normal direction. Here the normal direction is z direction. So the first index ij, the first index is the direction to which force is acting, and this is the direction of to which area is pointing, right? This is a thumb rule, you can specify that. Now the third cut section we can also think is this, that, and this, like yes, slantwise. So we can, yes, we can actually horizontal cut section. Again you can cut in this fashion, and you have the exposed area here, this one, and now you have several stresses, and one stress will be acting this way. So this is your tau, this is x, y, and z. So this is your y, right? So and this is your x, y, and this is your z, y. Okay, just to notice that these two things are not similar. So although these two things are, all these three things are acting in y direction, all these three things are acting in y direction, but all these things are not similar. Why? So this is your normal component, normal stress, but here this is your shear stress. Here also this is your shear stress, but in another direction, right? So all these components club together, and now it will be completely written over here. Like there are 9 components, namely I can write tau, I can write in this form tau xx, comma tau xy, comma tau xz, comma tau yy, tau yz, tau yx, tau zz, tau zx, and tau zy. So all these 9 components together should be specified. I mean, if you want to specify the stress on a point, on this particular point, you have to tell all these values. Otherwise, you cannot specify the stress on a point. Okay, you should have all these values in your hand. Otherwise, you cannot. Okay, so namely, so this thing can be clubbed and written into the matrix form tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. It can also be written as tau I, j. Okay, and this is how the second order tensor is generally written in matrix form. But the matrix, notice that matrix and tensors are nowhere similar. They are similar in just a way that matrix are just the collection of numbers, but these tensors are also the collection of those components, but they also obey some transformation, and we will look into now. how these tensors are related to the transformations. So in order to do see the transformation, how these are uh, written in transformation form, let's look into the 2D case first, and then it can be 2D case means we'll seek just a vector in two-dimensional space, and then we will step one ahead. We will go one step ahead and we'll tell that this also follows in the higher order also. Okay, so we'll see the rotation of axis, how the rotation of axis affects your vector. Okay, and we'll see now. So let's suppose I have so let's start with three-dimensional, then we will switch into 2D case for the ease of calculation. So I have, let's suppose I have these coordinates 1, 2, and 3. Okay, so from now onwards, we will show the coordinates with 1, 2, 3. Okay, and the components I will show from x1, x2, x3, and the unit vectors or the basis vector we will write as a1, a2, and a3, not I, j, k. Why? This will be reserved for tensor notation. Okay, and we should not be confused with these ijk's with the tensor notation ijk. Okay, that is why we will specify these unit vectors with a1, a2, a3, components with x1, x2, x3, and the coordinates with 1, 2, and 3. So let's suppose I have a vector x. I have some vector x, and also vectors I will represent as x bar, down bar, and tensor I will double bar in the all my future slides. Okay, this would be the notation I will be following, because I cannot write things in bold here, right? While writing bold, I need to do something like this, which is not a good way to write. So for specifying vectors, I will write x down bar, and for tensors, for higher order tensors, we should write double notation over here. Okay, and for more higher order tensors, let's suppose m is my third order tensor, so I'll write 3 bars over here. So this is what the convention will follow in this particular course throughout. Okay, so this is your x. So this x will have some component. Okay, so this x will have some component in x direction, it will have some x1. This component will have some component in 2 direction, that is x2, which is what I'm going to follow, and in third direction we'll have x3. Okay, these components are there. So for this vector, I am going to write in the vector form as x1 a1 plus x2 a2 plus x3 a3, and these notations are well written in your Kundu Cohen book. You should actually follow this book. So all these things are given. So in our usual notation, we usually how we specify x is equal to x1i plus x2j plus x3k, but here we will follow this notation for the sake of tensor notations. Okay, we will reserve these things for tensor notation. Okay. Now, can we write this as summation over xi ai, where I is equal to 1 to 3 in more compact way. So for any vector, can we write in this way? This thing can be written in summation form?
Yes, sir.
Okay. Now one more step I want to tell you guys, that in this particular course, this summation signs, all the times this summation signs is not desirable to write every time, because it will be very cumbersome. So whenever I see a repetitive index, these i's are repeated in my index, I'll drop this summation sign, and a new way to write the same thing is x bar is equal to xi ai, and this is how I am going to write the vector in all our courses. Okay, so this is essentially dropping this summation sign, dropping the summation sign all the time, because it will be cumbersome to write every time this summation sign. It will be whenever you see this repeated index, you will formally put that, you will formally understand that there will be a hidden summation sign is there, but we are not going to write, and this is called Einstein notation. During his relativity theory, when he was giving writing his notes, so he generally, you know, that physicists used to work in fourth dimensions, and they must be working with lot of components, like you can see that I, j, k, l, n components, and so many equations will be there. So that is why Einstein started this particular thing, to just to drop out unnecessary things in order to ease your calculations. Okay, so since we don't have much time, we will take up this thing in the next class, since we don't have much time. It's already 11:45, so I need to leave. I have another class also. So yes, we will take up in the next. So far, any doubt? So the idea is to go this thing into some transformation, and we'll see that how, when the transformation happens, when the coordinate rotates 1 dash, 2 dash, and 3 dash, what would happen to this particular vector x under this transformation, and then see that things are invariant and only the components changes. And this also suffice my statement that vector is a tensor, is a first order tensor, and we'll go step by step. Okay, so far any doubt?
No, sir.
Okay, okay, thank you.
Sir.
So let me take the attendance. So am I going too slow or fast or what? Can I have some feedback from you guys?
Regular speed, sir.
Okay, good.
Sir, it is regular.
It is good.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, okay, take it. Thank you.
Sir,
Okay, then.
actually,
So
we are
Monday
not
we
able.
do have class or not? We don't have, right? From Monday we don't have classes, na?
No,
सर
sir.
दिवाली वैकेशन
Yes,
कितने
sir.
तारीख
Yes.
कितने डेट तक है दिवाली
Let
वैकेशन
me
सर?
check. Let me check now. Let me check now.
सर मेल आ
सर
गया है
मेल आ
सर.
गया है.
हाँ, मेल आ गया मुझे, हम लोगों का ईमेल आ गया डायरेक्टर का. दिवाली वैकेशन फॉर स्टूडेंट्स फॉर excluding D2D students of same 3. So Diwali vacation for BTech, MTech and MSc students is from 16th Monday to 20. We'll resume the online classes from 23. Okay. Happy Diwali. That's a good news for you guys.
हैप्पी दिवाली.
Okay,
Happy
happy
Diwali.
Diwali. Chalo, so then
हैप्पी
we'll meet
दिवाली सर.
next to next Monday. probably 23rd. Okay. So till then, keep
Sir,
reading
any
this
chance?
particular book. Okay. Till then, keep reading this book, Kundu Cohen. This is so good. Try to read this book. Okay. It's everything is there here. What I taught today, everything is there. Okay.
Okay, sir.
Okay. Try to read this. Okay. Thank you. I have taken the attendance. Thank you. Bye.
Okay,
Okay.
bye.